Hi everyone, and welcome to the second of two videos looking at some past exam questions on concentration time graphs. Again, you can see we've got a graph here. It's a graph of concentration and time, funnily enough. And again, we've got a reaction. It doesn't really matter what the reaction is. Let's just go straight to questions and see what it says here. The student uses half-life to suggest the order of reaction. Okay, this is what we talked about in the first video. First of all, what is meant by the half-life? You might be asked to define this. Okay, and so the half-life is the time it takes for the concentration of the reactant to half. It then says confirm the order of reaction with respect to the reactant here. So we've got to work this out on the graph. As we did in the previous video, the way that we're going to work out the order of reaction is to look at the half-lives. Okay. So again, we could try and start here, but rather than trying to work out, okay, what is this, 5.6, 5.7, 5.9, we're going to do the same as we did on the first video and pick some nice easy numbers. Okay, so I'm going to start with 4. I'm going to go from 4 to 2, and I'm going to go from 2 to 1. Okay, so I'm going to start off here at a concentration of 4. I'm going to read across, and then we're going to read down where that comes to on our graph. And that looks like 22, 24, 26, 28. That looks like that is 28 seconds. And then if we read off from concentration of 2, that's going to come to 80 seconds here. Okay. So this is our half-life from 28 to 80 seconds. Remember that this gap here, this is not a half-life. That doesn't represent anything. Half-life has got to be the time it takes for the concentration to halve. Okay, and so the half-life here is 52 seconds. And then we're going to measure the half-life again. I'm going to go across from 1. And I'm going to go down from here. And that to me looks like 122, 124, 26, 128, 130, 132, 134 seconds. So we've gone from 80 to 134. So that is 54 seconds. Okay. Now we should, as we said in the previous video, we should really go to 0.5 and work out a third half-life to be confident of our conclusion. But 0.5 is not quite going to fit onto our graph here. And these two half-lives are so similar to each other that I feel like we can be fairly confident in saying this half-life is staying constant. Okay, there is very little difference between those. Okay, so I'm going to go ahead and I'm going to say the half-life is constant at around 52 seconds. Therefore, the order of reaction with respect to our reactant, which was the benzene diazonium chloride. Don't worry too much about what that is. It's not something you're expected to know. Is first order. Okay, remember if the half-life is constant, it's going to be a first order reaction. Okay. So very similar to what we saw in the previous video. Okay, you're going to work out your half-lives, and that is what is going to determine what the order of reaction is. This question then continues. It then says, what would be the effect, if any, on the half-life of this reaction of doubling the initial concentration? Okay, what do you think? Well, if it's going to double the concentration, that's going to affect the rate of reaction. But what have we already said about the half-life? Okay, we just wrote down, didn't we, in the previous question, the half-life is constant. Okay, and so this is kind of like a trick question, right? We've just said the half-life is constant, so it's not going to have any effect on the half-life. Okay. We've just said it's a first order reaction, the half-life is constant. So that is not going to change. The student predicts that the rate equation is this. This all seems to fit with what we've said so far, right? It's just showing it's a first order reaction. So this is a good clue that we were actually on the right track with what we said from the earlier part. Using the graph and the rate equation, determine the rate of reaction after 40 seconds. Okay. So if we want to work out the rate of reaction, the way we're going to do that from the graph is to draw a tangent. Okay, but it's slightly different. In the first video on this topic, we were calculating the initial rate of reaction, so we drew our tangent on the graph right at the start. Here we're determining the rate of reaction after 40 seconds, so it's important that we draw a tangent at 40 seconds. Okay, just be careful there. So we need to go back to our graph. We need to find where 40 seconds is. Actually find the right line, which is here. And we are going to draw a tangent at this point. Again, just want to take some time making sure that it is actually parallel to the graph at this point. Okay. And then we want to draw a tangent. I always just carry the tangent on all the way up to both axes. When you're calculating a gradient like this, you want to make your kind of triangle as big as you possibly can. If you draw like a little triangle here and try and work it out, if you're one square wrong, you end up with a big percentage error and it makes a big difference to your answer. Whereas if I'm one square wrong over that distance, it's going to make very little difference to what the actual answer comes out as. So make your triangle as big as you possibly can. Then if we're going to calculate the gradient, remember we're going to do the change in y over the change in x. So on the y-axis, if you go all the way down, you can see it goes to 0. So all I need to do is read off this value, which is 5.1, 5.2, 5.3. Just check on the axes that there's no like times 10 to the minus 3 or anything sneaky like that, which there isn't this time, so we don't have to worry about that. So 5.3 there, and then on this axis, we've got 116 seconds. Okay, so I'm just going to go ahead and calculate that. So we're going to do 5.3 over 116. And we're going to get a value of 0.0. Does it say anything about significant figures? No, it doesn't. We don't need to worry about that for this question. So we'll call this 0.046. It doesn't say standard form or significant figures or anything here, so we don't need to worry about that. And units, what have we worked out? We're working out rate of reaction, so the units are going to be moles per decimeter cubed per second. It then is asking us to calculate the rate constant. Okay, so to do that, we're going to use this rate equation that they've given us. We're going to rearrange it. Okay, we've seen this before. So the rate constant K is going to be equal to the rate divided by the concentration of C6H5N2Cr, benzene diazonium chloride. Values we need to substitute in. We're going to use our value for the rate that we just worked out. And then for the value for the concentration, this was the rate after 40 seconds. So for the concentration, we need to work out what is the concentration after 40 seconds. Okay, we can't just use whatever concentration we like. We need to have a concentration and a rate from the same point. Okay, so again, we need to go back to our graph. At 40 seconds, what was the concentration? If we read across here, 3.1, 3.2, 3.3, 3.4, 3.45, I'm going to call that. It's just coming up between 3.4 and 3.5. So we go ahead and calculate that. I've still got my number on the calculator from before. Okay, so it's good practice. Don't delete these numbers off if you can avoid it. So I'm going to use this whole number. Okay, I'm not going to use my rounded value that I've put here. I'm going to use the whole number that's on the calculator. It's always a good idea. Divided by 3.45. And we're going to get 0.013. And again, doesn't mention anything about significant figures or standard form or anything like that. So we can just go ahead and use that. And then units. we need to put the units in here. Units of rate would be moles per decimeter cubed per second, as always. And then concentration is moles per decimeter cubed. So we can cancel one from top and bottom, and we're just going to be left with units of seconds to the minus 1. Okay, part C here then says, the order of this reaction with respect to H2O is effectively 0. Explain why. So for this, we need to understand what 0 order actually means. 0 order means that when we change the concentration, it has no effect on the rate. Okay? But that's not the answer, that's just explaining what 0 order means. What the question is asking us is, why is it 0 order? Okay. Well, the reason why H2O is 0 order is because the concept of changing the concentration of H2O doesn't really make any sense, right? The concentration of something is how much of something you've got dissolved in water. You can't have water dissolved in water. What is the concentration of a solution of water? That doesn't make any sense. Okay, so you can't change the concentration of water. Okay? So that's all it wants us to say for this question. You're going to say the concentration of H2O does not change. Okay, that's kind of a meaningless idea anyway. You could say an alternative way of wording that is just to say that the water is in excess. Yeah, you've got, in any solution, you can have so much more water than you are of whatever's dissolved in that solution, that it's going to be in such a large excess that increasing the concentration of water a bit more is not going to make any difference, because there's so much of it there already, it's not going to matter. We'll come on to more of those ideas later on when we start looking at the idea of a rate determining step, but we'll get to that in some later videos. And then finally, just to finish off here, we've got a multiple choice question, which is getting at the idea of half-lives from a slightly different angle. We've got a reaction here, and it's saying it's first order with respect to this reactant AB, and it's telling us that the half-life of the reaction is 2 minutes. 0.1 moles of AB is dissolved in a solvent to form 100 centimeters cubed of a mixture. What is the concentration of AB after 6 minutes? Okay. Now we need to be really careful here. The first thing we need to do is work out what's the concentration at the start. Okay, because it's not 0.1, because we had 0.1 moles in 100 centimeters cubed. Okay, 100 centimeters cubed is 0.1 decimeters cubed. Yeah, remember we divide by 1,000 to get it into decimeters cubed. So therefore the concentration initially was 0.1 moles over 0.1 decimeters cubed. So the initial concentration was 1 mole per decimeter cubed. Okay. Then if it's telling us that the half-life is 2 minutes, that means it takes 2 minutes for the concentration to half. Okay. So after 2 minutes, the concentration is going to be 0.5 moles per decimeter cubed. After another 2 minutes, the concentration is going to be 0.25. And then so after 6 minutes, we've had 3 lots of 2 minutes go by. And so the concentration is now going to be 0.125 moles per decimeter cubed. Okay, because we've gone through 3 half-lives. It's halved, and it's halved again. Okay, and so therefore the correct answer is C.